Yeah, I'm Brian Englekemier. I am a flight software architect at Northrop Grumman in Baltimore. My co-author is Chris Mason, was a software engineer on the team of the program I'm going to be talking about. He could not be here today for this. We're going to talk about the benefits of a virtual systems integration lab, or VSIL. In order to tell you about this, I'm going to walk you through the chronology of how we built it up, what we discovered along the way, and how it worked out for us. Okay. So, why would you want to invest in a VSIL? As I'm sure most of us know, the EDU test benches that you get for building systems, they're expensive, they're limited, so you get one or two. There's a lot of demand for it with people from different groups that need it, from the integration and test teams, the flight software teams. Lots of people need access for that. Because of that, our program was seeing our schedule continually pushed to the right. And we reached a point where software was on the critical path, and we wanted to fix that. We didn't want us to be the problem. So we started investigating how to fix this, and we discovered within Northrop there was another team that was doing some virtualization work, and we looked at what they were doing and convinced our management to invest in building this virtual system integration lab for us. So we then started working on it. So what is it? It's our implementation is a hardware simulation using Wind River Simox that runs unmodified flight software binaries. It simulates the hardware from the software viewpoint. Yeah, I know some people here know Simox. We were going to call some of them in if we couldn't convince our management that this was worthwhile doing. Each user gets their own platform on their own desktop PC, so suddenly instead of 2 benches, every developer has one. You can run, as we'll show later, you can run flight software, test software, INT can use it, hardware verification teams can use it. So when we decided to invest it, we took 4 people and got our virtual payload up and running. It took about 6 months to get it running fully for flight software. It only took about 2.5 months for flight software to just start using it and start poking at it and seeing what was good, what wasn't good, what did we need to fix. And to give you an example, this isn't really our payload. Our payload has multiple single board computers, has 8 custom boards, and the total board count for mission requirements, to meet mission requirements and reliability and redundancy is more than 25. So that's why it took so many people that long. So Simox is the technology that enables the VSIL. Simox gives you models of all the pieces of the boards. It models the memory, it models the flash drives that we use. It models the devices. There's chip level models. One of our boards has a 1553 interface. We could use the existing on a 1553 on a chip. We could use the existing model for that, excuse me, and just drop that one in there. It runs everything from the kernel through the board support package, the flight software, all of it runs unmodified, so you can use it for all of those kind of things. There's no custom compile switches. The binary takes from there and goes and runs over on it. So it provides, one of the first things after that initial 2.5 month period when we started getting flight software on it, we started seeing some of the benefits right away. You could do kernel work, BSP work, and flight software development, all of it on there. It's an accurate hardware environment, so you can do all of that. You don't have to, well, let's wait until we can run our kernel on the right one, on the real system, and see what's going on. The model runs like we said, all of it without modification. Another big benefit we saw right away is that you debug by stopping the entire system. The models all stop. No more interrupts coming in while you're looking and trying to poke around. You can examine the state of the boards, where they are when you stop it. You can reverse the execution of the system. Our system is not really a hard real time, it's more just in time. So sometimes you end up with things running in different sequences. And how did I get there? How did I get there? You can stop it and back up and see what happened. How did you get there? So within 2 hours, we had a problem that was plaguing the team for 6 months. We had this random crash. It would happen like 3 times during a day, then we wouldn't see it for a month. Then it would happen again. We saw it, fortunately we saw it in the first few weeks of running the flight software on the VSIL. Once we saw it, we could, now the board was not hung, we could look at it and see what was going on, figure out where we were. 2 hours later, we had the root cause nailed, and we could fix it. That right there made it worth it, just for that. It's also great for fault detection and insertion. We could add in our boards, the boards model the connections between them. So you can have checking in between there. You can have checking on the board to say, when you write to this register, 1 second later, you have to write to this one. If you're writing too slow, too fast, you can do that. You can test that in the model. The model can alert you when those kind of things happen. So you can get timeline verification. You can insert faults from the hardware boards through the VSIL, because you can build an interface from the models themselves into the board. One of the biggest uses we've had for it, for doing that, is we can insert flash memory faults. Our boards have a flash drive that at boot up we load the flight software from. So we're able to insert block level recoverable and non-recoverable errors and make sure that flight software detects it, that the kernel detects it, that flight software detects it, that our recovery operations work. We can do all that without damaging any piece of hardware. Let's see what that. So our big selling point was to tell management, we're going to pull the schedule back. But that's kind of a wishy-washy thing. So the way we tried to tell it was by tracking cost avoidance. So basically we said, we put in a timer so that we knew when developers were using the VSIL and we knew how long they were using. And we were trading that for hours towards the end of the schedule to try to pull that back in. And we were also tracking at the same time real hardware availability to say, one of the hardware guys took the bench and took it apart, so we couldn't use it for 3 hours that day. So those are 3 hours we didn't have it, that we did get more, that we got more benefit from having the virtual SIL there. So we used that to track it. And then that's also tracked against the cost of the standing army at the end of the program when, sorry, you only have 6 hours, not 6 inches, 6 hours of time on the bench, but you've got the entire flight software team there for 8. So that's a standing army that you have to absorb those kind of costs. So as you can see on this chart, maybe not. So we broke even about 4 months into it, and at 6 months we doubled our return on our investment, and it's been continuing to grow since then. I think a better marker of pulling the schedule to the right is that, so we started this in 2014. We have had the VSIL running all of 2015. Earlier this year, we had board flight software engineers because we were meeting all of our requirements, and we haven't gotten to payload INT yet. So we're now using them to work on the VSIL, to work for building new capabilities that we were going to be delivering after delivery. So I think that gives a better answer than this, but management likes to see this kind of thing. So before I can go into some of the other benefits, I want to talk about our testing framework that we have. It's Atlas, which is ATL, which is the building we're in, an acquisition and analysis system. It's a reusable framework for testing, performance testing, functional testing, calibration testing. It works everything up from board level INT all the way up. We track all of the information. It provides control of the STI that you need, control of the payload or the unit under test. Gives one-touch control from the operator's console for running all of these things, and it provides automated pass-fail. When you do an analysis after the acquisition, you get it, and it's all stored. All of this is stored in the database. It also stores all the telemetry from the STI, all the telemetry from the payload, as well as the payload output files. And the results of all of these activities are stored, so you can do a lot of data mining to go find out what you've got. So why would we want to use Atlas with the VSIL? When you look at the VSIL, it's not just a flight software tool. It runs flight software. But now that it's running flight software, it can be used by people that need to use flight software to do their tasks. So you could do system and flight software test development. Atlas runs tests that are go run this scenario, so you feed these files into the payload, this is the expected output. All that development has to happen. And previously, that was one of the things that was tying up the bench. So again, the test software team now can use this. They now have a fully functioning payload on their desktop. So they were using it. So that's for both flight software and system test and development. We wanted to capture all of those to track the problems. Where did we start seeing this problem? Somebody thought they saw it 3 weeks ago, but we weren't sure. So we wanted to track all of those, and that's what's always captured in the database. We also have hundreds of existing testing scenarios right now, and we want those to be able to be run by anybody. The flight software team should be able to run performance tests and make sure that we're still doing that. So instead of writing their own version of that to feed in with a different tool, we want to be able to use Atlas. So to integrate Atlas with the vSIL, we first had to take out the STI, but that's not a problem. Atlas is built to be configurable from the ground up, from when you first start getting pieces showing up all the way up to the full payload. So that was not a big problem. Then we have to replace the unit under test with the vSIL. So we pulled it out and put it in. That was a little bit more. We had to teach Atlas how to run the vSIL, how to spawn it, how to talk to it. The bigger problem was there's a bus emulator that's part of Atlas which feeds the 1553 into the payload. The 1553 is no longer there. It's a virtual 1553. So we had to have the bus emulator understand how to send messages into the vSIL model, and the model then places them into the 1553 chip at the right time. And the right time being the vSIL time, not wall clock time. When you're running in the simulator, there's at least two different time bases you have to keep track of. One is what's the payload time, and one is what's outside time. So that was a little tricky to get it going, but once we got it going, it's been rock solid since then. So we're going to go back and look at why really run with it. The real reason is our release rhythm. For flight software and test software, we were doing weekly or fortnightly builds, and we were doing full regression tests, or partial regression tests on those. We had an engineer coming in at 2 in the morning to run those. That's just not right to do to somebody. But that's the only time we can get the bench dedicated for 8 hours to run all these tests. And then monthly, we're doing the same kind of thing, except we're doing full up regression tests, not targeted ones based on what changes were made that week. So we wanted to replace this with nightly automated testing, which is really nice because now nobody's worried about the hardware. It's not expensive. It's not going to go over temp. You're not going to have to worry about the power supply going wrong. So the first thing to do is we got to take away the operator console from Atlas. It's the easy command line parameters. And the next one is we replace the operator with Jenkins. Jenkins, if you don't know, is an automated server to take out the non-human parts of software development. So it's perfect for this kind of thing to run that for us.
What is the operator doing?
Start up the unit, monitoring. So the test software, the flight software, monitor the payload and make sure everything's going okay. The operator's there looking at the displays going, yeah, the temps still look okay. Both of the software systems are supposed to shut it down if you're having problems, depending on the severity of the problems. But we don't want to trust that while it's in our hands and while we're developing all of this. So the operator's saying, go run this test. The results come back, go run this test. The operator is also the flight software engineer, the test software engineer. So they're going to run that test. Oh, no, recompile, reload, redeploy, run it. So that's what it is. It depends really on where you are in the system. So we replaced Jenkins. So implementing the automated testing was not that big of a deal. Jenkins is really nice to use. We previously had nightly builds going on with the results being emailed out just to see who broke the build on the latest check-ins. That was done as a cron job, so first we had to make Jenkins take over that. Once he did that, then we've got the full cycle, and in fact there's one more step in there that we've got, which is we do static code analysis as part of the nightly runs too. So that's also what Jenkins does. We run it on multiple baselines. I said we split the flight software into 2 baselines so we can work for future capabilities as well as the ones that are needed at delivery. He's also running testing flight software and testing test software at night. The results, we have a subset of the full tests that run nightly. On the weekends, we run a full set of tests because it takes longer than just an overnight run. It starts around midnight. Developers get the email results from Jenkins every morning. At 7 o'clock, it shows up in your inbox telling you what's broken. There was one other thing on this, don't remember what it was. So, other benefits. So, because of our success on our program, other programs are starting to look at this. One program I'm supporting, we have the FPGA designers, the model developers and flight software defining the model behavior, get to define what the FPGA is. Like, traditional development at Northrop is the hardware and the FPGA get done really early, and the FPGA guys are gone by the time flight software gets there, and now we've got to live with what they thought we would want. Now we're working that at the same time, so we're shortening our development cycles, we're shortening our programs. That's working out really well. Even the FPGA designers like it because they now know what we do with it, they understand it, and they can start suggesting things. The hardware engineers that are doing the hardware INT, they're developing their acceptance tests. The VSIL doesn't really have to run flight software, it can run anything. We run unit tests on it. It runs any piece of software you want to put at it. So the hardware engineers are writing their acceptance tests to test that FPGA interface. Using the VSIL, they can do it without the boards being there, and then when the boards are there, they've got a better shot at finding the bugs. It helps cut down their times as well. And we're getting to the point that we're going to have flight software running on the hardware before the hardware is available because of the VSIL. And that's our goal. So in summary, the benefits are it's a better development environment. It's accurate hardware. It works everything from kernel all the way up through flight software as well as other types of software. We can do fault insertion that we couldn't do before without going in and tweaking code or something like that. We can stop the entire system for debugging. We can do the reverse executions to find out where we got to. We're cutting down on cost and schedule because a lot of it is because of the ability for all these other software teams, even the ones that didn't think they were software, like the hardware INT guys, they're able to use it, and we can start flight software development before the hardware is available. And we're seeing an increase in reliability with the automated unit regression and functional tests. We get much more test like you fly capability now because we can just increase the number of tests. Fault insertion and full payload is always available. With all the boards, you can imagine our EDU units are never fully populated. Now we have a fully populated system that we're able to run on. And I remembered what it was about the Jenkins. Chris Mason, who was the one that worked on that, added in, we run it off of a spreadsheet. It's driven off a spreadsheet. So anybody can add a test to run. They just put the name of it in there and then go say what days they want it to run. Nobody has to worry about knowing how Jenkins scripting. Less programming language to learn. We don't have to worry about teaching people that. It just works then. So what are our lessons learned? As with every simulation, you want to start small in your model first. We started with just flight software required. We grew from there, and it still gave us a lot of benefit at the very beginning. It still doesn't replace the full payload. Once we got onto the full payload, we had 4 minor bugs that didn't take us much time to figure out, and they were all timeline related, which then is another lesson learned is VSIL is another source of bugs. It's another piece of software, so you've got to monitor. If you see a problem on the real payload, but you don't see it in VSIL, you have to figure out why, and then feed that information back into the VSIL and get new revs on it. And iterate on the timing of the model. The board models need to provide the same timing as the hardware. But you don't have to do that right away. It doesn't have to happen right away, especially if you start really early. Just get close enough so that everybody gets a feeling for how things are going to work. And that's it. Have any questions?
There are actually a lot of people listening online, otherwise they wouldn't.
Yeah.
So one question, two observations.
Mm-hmm.
Did you guys do your own models? Because I know how hard.
Yes, we did our own models.
Probably pretty intense.
So the SBCs, most of the pieces were there, but we had from various other places. But the rest of them, we had to do our own models, modeling all the connections between them. Some of the FPGAs have some really complex information that they have to fan out to other boards or feed back to flight software, and we're modeling that.
And then without, I hate plugging Wind River,
Uh-huh.
charging up. But the thing that was critical for us when we did that the first time we got Simox is the Indian issues, which I don't think a lot of people are aware of. So if you're trying to simulate on a big Indian and running on a little Indian or vice versa, the old VX Sim just doesn't work. It'll kill you.
Yeah.
And Simox is awesome. And then another thing is wild memory rights.
Mm-hmm.
So you don't have to have an ICE unit. You know, you don't have to spend $30,000 for an ICE. You can just literally put a breakpoint on right.
Yep.
So it's,
Yep. Yep.
Sounds good. More questions? Here, we'll go with this one.
So are your tests portable to any versions of hardware in the loop testing? So can you take the same test script controls and run the same models, but with whatever your versions of hardware in the loop platforms you have?
Yes, the tests are, yes. Between programs, they may or may not be. But so we can run the same script on the vSIL as well as on the real hardware, if that's your question, yes.
Yeah.
Yep, that's been our goal. The part that really cares about that is generally Atlas, part of Atlas, which is not the scripting part. The scripts are separate, so.
So on the model development,
Mm-hmm.
looking for a little insight into the scope of that work, relative to either the FPGA design effort versus the model design effort, and how you staffed it. Did you staff it with more software folks or hardware folks? What worked?
So
and what didn't
we've
work
staffed
there?
the model development with their software folks. And most of them are interns. We had a couple interns doing it. We had some right out of school doing it. Level of effort is certainly less, for a model, is certainly less than the FPGA, because you don't have to model all that the FPGA is doing. You just have to model the part that the software cares about.
what about compared to, say, like the device driver or that device?
It's probably more complex than that, but our device drivers are pretty simple for our architecture.
Other questions? Yep.
Could you give us a better idea of the level of effort that it took to develop the vSIL? How many people, how long, and how much effort did you spend debugging the vSIL as opposed to debugging the flight software?
So, like I said, the vSIL was the 4 people full-time for 6 months. What we were modeling were existing boards, so we already had the acceptance tests that the hardware INT guys run. So we ported those into the vSIL and ran those as a test of, is that interface what we need it to be? Then after that, I couldn't really tell you about debugging one side or the other, because we were spinning so much on, oh, this is great, I need it to be able to tell me this. And that just gets lumped in with, fixing a bug or, determining where the bug is, so. Sorry.
Other questions? No? Yes? No? Okay. Thank you.
Thank you.